In this video, we'll make the DWSIM model of gas turbine, which is basically a Brayton cycle. Brayton cycle depicts the air standard model of a gas turbine cycle. Brayton cycle comprised of three main components: compressor, a combustor, and a gas turbine. According to Brayton cycle principle, air is compressed in a turbine compressor or simple compressor. Air is then mixed with fuel. In this example, we'll use natural gas as a fuel, which is burned under a constant pressure conditions in combustor, and we'll consider adiabatic combustor in DWC model. The resulting hot gases are then allowed to expand through a gas turbine to perform work. Most of the work which is produced in gas turbine, for example, here 90 megawatt is used to run compressor, which needs 52 megawatt of work. So total work is work produced in gas turbine minus work needed in compressor, which is 38 megawatt in this case. A gas turbine is used in so many industries, so it is good if we can model it here. And I will also try to use some logical blocks, controller block to control the amount of air required, and also specification block. So let's jump into that. We will go for new chemical process model. As I mentioned, we will use methane as our fuel. So methane, we will select as a component. We also need oxygen, nitrogen, as an air components. Then we need carbon dioxide, and we will need water. For simplicity, I will only use these components and I will not add argon, etc. in air. For components, we will use Simpan Pang Robinson property package. And for units, you can use whatever you need. And I will use this temperature in degrees centigrade, mass flow rate in kilogram per second, pressure in bar, and we can also take work in megawatt, energy flow in megawatt instead of kilowatt. Okay. We will not disturb anything here. And then there's a simulation environment. So first we will need an air and air compressor. So we need a compressor here. Let's make it a little bit shorter. Okay. So there are two streams, two material streams and one energy stream in compressor. We will name it as air. And also I will use random mass flow rate here, so which you can change it according to your own needs. So this is not a real gas turbine which I will model there. So air stream 2, you can name it accordingly. In DWSIM, you need to enter everything while writing it, otherwise it will not make any changes. And this we can name it compressor. And And red in DWSIM means in the flow sheet is not completed. So mass flow rate I will use 80 kilogram per second at 25 degrees centigrade and 1 bar. For compressor, we need outlet pressure of, for example, say 30 bar or 25 bar. Efficiency, we will assume 85%. So now it is green, so it is blue. So it means our model for air compressor is fine. So to compress a 80 kilogram per second of air to from 1 bar to 25 bar, we need 26 megawatt of electricity in compression with 85% adiabatic efficiency. If we increase the efficiency, then the amount required uh, to operate compressor is lower. And outlet temperature of air is now 137 degrees centigrade. Which is lower. So we are making some mistake because compound is mixture is equalized. So we need to use it air. So I will clear everything, and air is 21% oxygen and 79% nitrogen for simplicity. And you need to accept it. And now we can see the stream condition. Yes, that is fine. 525 degrees centigrade, which is reasonable here. And after air, you need natural gas stream. I will use it as a natural gas, and again compound amounts. We need to change it. I will clear it. And I will use only methane here for simplicity again. And here you need to enter natural gas stream conditions. I will use 2 kilogram per second, 25 degrees C, and let's keep it at 1 bar. Now we need to mix both streams. We need to delete this auto generated streams 4 and 5. And we need to connect air stream 2 and natural gas here. And outlet stream 6 is fine. The one thing you need to make sure in mixer is in DWSIM is a pressure calculation. For example, natural gas. I need you can solve it. Yes, natural gas is at 1 bar and air is at 25 bar. So stream 6 is also at 1 bar. So in mixer, you either increase the pressure of natural gas to 25 bar, or you can use inlet maximum. So that pressure will be now it's 25 bar. And now you need a reactor. And for combustion reactor, we will use Gibbs reactor here. Inlet stream is 6, which is fine. And outlet streams are 7, and 8 is liquid stream, which is normally dummy because we are only using like all the all the compounds are in vapor phase. So I will just name it dummy stream. So there will be no liquid or fluid here. And calculation mode is adiabatic, and we will have zero pressure drop here again for simplicity. Now for compounds, we need all the components here. And if you are using, for example, other components which we will not include it here, then you have to select it accordingly. Elements again, they are fine, and then we will solve it. And it is giving invalid estimates. Compounds, elements, they are fine. Convergence. It is not solving. So, okay, let's choose outlet temperature. And let's use 1200 degrees centigrade. Okay, now it's solved, but it should be adiabatic. So now I will choose adiabatic again. Okay, now it is solved. And energy should be zero here. It is taking its time to solve it. Okay, now it is solved. I think they made some changes in new version, which is a little bit slower. I hope they will solve it later. And now temperature is 1400 with energy flow of zero. It means it's an adiabatic reactor, which is fine. And we can change the temperature by increasing or decreasing the air flow rate, which we will discuss this later. And now we need a gas turbine as a last component in our Brayton cycle. We will use expander here. And another problem with DWSIM is it automatically connects the inlet and outlets, and sometimes they are wrong. For example, we do not want dummy here. We want this stream 7 because dummy is having zero mass flow rate. So we need stream 7 as inlet stream. Outlet 9 is fine. And now we have to reduce the pressure from 25 bar to 1 bar. And we will name it gas turbine GT. And then solve it. It should be solved automatically, but I do not know why it's not getting solved. Okay, now we have here. Yes, it's here. Energy flow rate of 71 megawatt from gas turbine, but this is not our electricity output because we need to provide the same electricity to compressor. So 71 minus 42, approximately 28, 29 megawatt will be our power output. Or we can do it automatically by using energy mixer there. We can add E3. We cannot mix even there, so we need to add another one, which is E1, but duplicate. I will name it duplicate. So how to do it automatically? How to use 42 megawatt here? We can use a logical block, specification block, which is easy. So our source object is E1 from compressor, and source property is energy flow. And our target is E1 duplicate, and target property is also energy flow. So Y means target object should be equal to minus X. So minus 48 megawatt will be there. And output will be total power. See, now 71 minus 42 total power is 29 megawatt, which is an easy way. So why we need it? Because we can now change amount of air and natural gas. We do not need to calculate every time what is the total power from gas turbine. And as I mentioned earlier, we can check in exhaust conditions. Our air is at 11% excess. How we can increase or reduce the amount of air? You can do it manually, or you can use a controller block, which is easy. So in controller block, we need to manipulate air, mass flow, and we need to control stream 7 mole fraction of oxygen. We need to go down, 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 and find the mole fraction of air in vapor condition, methane, 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 and oxygen, molar fraction of air. And set point, you need them at 14%. We can start adjusting it. So remember the amount air flow rate is 80 kilogram per second. So we can see if it works or not. Sometimes it does not work. Let's wait. And this is where DWSIM is little bit lacking as compared to other process simulation software. For example, in Aspen Plus and Aspen Hyaces, this is really quick. You can manipulate so many objects. You can manipulate multiple streams, and but here these are a little bit slower. But it is free, so we can live with it. And sometimes it feels you can change the amount of air manually, which will be a little bit faster than instead of dealing with. Yes, it is solved now. For example, now you can see its excess amount oxygen is 14% as we mentioned in controller block, and air was 80 kilogram per second, but now it is 109 kilogram per second. And temperature was 1400, but now it is 1200. So you can play with it accordingly, and if you want to do me some other changes, I can suggest in later videos. And exhaust temperature is 631 degrees centigrade, which should be utilized for heat recovery, for example, steam generation, which I will also model it in later slides, continue this model. And yes, and other things that you can do, you can add a property table there. For example, here you can mention compressor power required, gas turbine power generated, so that you can see, and you can also add properties for air, natural gas, and stream 7 and 9. 7 is before gas turbine and 9 is after gas turbine. Here temperature, pressure, mass flow, and molar fraction, methane, molar fraction, oxygen, molar fraction, nitrogen, or whatever you want. Molar fraction, carbon dioxide, and at last molar fraction, water. Yes, so yep. Now you can visualize these properties here. So if you like this video, subscribe for more videos like this, and we'll see you in our next one.